Okay, so thank you everybody for coming, and let's get started. So thanks again everybody for coming. My name is Jamie Fine, and welcome to the March edition of our guest lecture series, the Climate Science for Engineering guest lecture series. For those who are interested in commenting or having something to contribute, please feel free to use the chat that should be enabled. You can also put your hand up if you have something to say too, but please just put your message in the chat. So for those who aren't yet aware, the CSE is the Center for Climate Science and Engineering. We are a research and educational center at the University of Toronto, housed inside the Civil Engineering Department. And the center was established back in 2019. And the center is made up of several faculty members from different departments, actually, that cover a bunch of the different disciplines that we feel really contribute to solving climate change related problems from an engineering perspective, especially. And on this slide here, you can see the CSE team. So the center director is Oya Merkan. And then the other executive team members are Marian Hatzpalu, focuses on transportation. Paul Kushner focuses on climate dynamics. Graham Norvell focuses on health and process safety. Daniel Posen on life cycle assessment. Karen Smith on atmospheric science. Marian Tucci on building science. And then myself, where I'm the CSE manager. Okay, and so as you can see, we have a lecture series. So we have different educational activities that we carry at the center, and one of them is these lectures. So we invite guest lecturers in once a month to give a presentation about a topic that's related to the CSE. Today we have one from King Tung, a presentation from King Tung, and we will have one next month in April from Diane Sachs. Diane is an environmental and climate science lawyer, and she's also the deputy leader of the Ontario Green Party. We expect that presentation is going to be about which climate solutions work and what else can they make better with respect to these solutions. So that's the guest lecture series that we have. And then on top of that, we have workshops. So we have 2 more workshops that are remaining this year. Currently, these are only open to U of T students, but in the future, we're looking to expand these workshop offerings to make it to external of U of T students. And the one that's coming up in mid-April is going to be by Professor Marian Hatzpalu, focusing on transportation. And then we have one more in May, and that's going to be from Professor Daniel Posen, and that's going to be focusing on using life cycle thinking to inform climate policy. Okay. And I think that's it for the housekeeping, but now just to introduce our presenter. So our speaker today is King Tung. He works at Enwave Energy Corporation, and he is an energy system analyst in the community energy planning team. He also has a master's degree in mechanical engineering from Ryerson University, and during his master's, he researched net zero transitional technology for the residential sector. Currently, he is working at Enwave, as I mentioned, from back in 2019, and he's focusing on projects across North America, developing sustainable and resilient district energy systems for new developments. And right now, he's working on several nearly net zero projects, which leverage existing technologies such as geothermal exchange and sewer heat recovery, along with the benefits of district energy. And today, he's going to talk to us about decarbonizing cities with district energy. Did I miss anything there, King?
No, that's perfect.
Okay, great. So please, everyone can welcome King, and please take it away.
Thank you, Jamie. And let me figure out how to share screen. Give me one moment. Let's see. And tell me when you see this.
And right. There we go. Yep, I see the picture.
Okay. All right. Hope you guys are doing well. So like Jamie said, my name is King, and I work at Enwave. Enwave is a district energy provider, and we provide district energy services across North America. And I'm part of the CEP team, which is the Community Energy Planning Team. I work as a system energy analyst. So the CEP team kind of plans, design, and facilitate new developments that are located too far away from existing development systems. So we call them like a mini district in a sense, and it's kind of like a mini district system. We call it district nodes, and kind of want to talk about that and how it's helpful to use that to decarbonize city. So first off is I want to gauge everybody's knowledge of district energy and have a question. Let's see, how do I put the poll on? So I wanted to ask everybody, you know what district energy is? Just mainly to kind of test out this function, but we'll see. I'll give another like a minute or two. Should see it like a pop-up somewhere. Think that works. Pop up somewhere and select. Give another moment or so. Right. Okay, I guess that's it. All right. So 9 people kind of understand. So a majority of you guys know what district energy is. Cool. And kind of half of you either said no or no response. So let's continue and let's start with a quick video.
I don't think we can hear the sound, King.
Really? You can't hear it?
No, I don't think so. You'll have to narrate it yourself.
King, sorry, just to jump in, apologies for the interruption. If you want to reshare your screen, there's a little button on the lower left-hand side that says share audio, and that should work.
Yes, that would work. All right. Let's try this again.
Is there a better way to heat and cool buildings? When it comes to heating and cooling, many buildings house their own equipment. They need enough equipment for the very hottest and coldest days ever. All those boilers, chillers, and cooling towers installed on their property, even if some are rarely used. All of this takes up valuable space, but it's also capital intensive, has poor utilization, and often is not the most sustainable. That's why leading building owners, communities, and campuses are choosing something smarter. A district energy system connects buildings to share common heating and cooling equipment. This gives buildings higher efficiency and lower capital costs. It enables new spaces for leasing and attracting higher value tenants. Think of it as virtual energy. This district solution enables sustainability at scale by taking advantage of other forms of energy, anything from upcycling waste energy to deep lake cooling to biomass or geothermal. The peak energy demand of a district can be reduced significantly. For example, using ice batteries to store energy off-peak when the grid is greenest and lowest cost. And the district energy solution conserves water by making smarter use of it. But what happens when new technologies come along? With district energy, you can upgrade all the connected buildings at once, future-proofing communities and campuses, helping them meet their sustainability goals. District energy delivers the benefits of scale, reliability, and sustainability while creating new revenue opportunities. District energy, because life is better connected. Learn more at enwave.com.
All right. So, to summarize what district energy is, so I don't have to explain it too much, and it's a nice quick video summarizing what DE is. So I believe that district energy is a future for city to decarbonize, and I'm not the only one who kind of believe that. Here's a quote from the UN. So more than 70% of the world's energy is consumed in cities. Almost half of it is for heating and cooling buildings. And one of the best ways to address climate change is through district energy. So I'm not the only one who think district energy is kind of like the technology to move us forward in decarbonizing. And there are many ways of using this technology to decarbonize cities. So I'm going to go forward with that. But first off, kind of want to see the scale of Enwave and kind of see how many systems we have so far. So this is kind of like the main systems that we have. We have roughly 4 main systems in Canada. We have the Windsor, we have London, we have the Charlottetown, and of course we have the Toronto ones. And we also operate in 4 of the most populated cities in North America. And we provide either cooling, heating, or sometimes both, and a little bit of electricity with the CHP. Okay, so next up, I want to talk about the community energy planning. So this is kind of like the main part of it. So what do I do, and what do we kind of, how do we figure out ideas to decarbonize cities or new developments or communities? So we basically need to improve our envelope. So that's usually the main thing. Like Enwave, we look at it as a node, and we have new developments. We first, of course, need to be competitive with the existing technologies, and there are many ways of reducing carbon, and these technologies are already existing, but we just have to use it with a different approach and kind of implement it differently. So these nodes are often too far from existing systems, so we cannot connect it to our main district system, but they are usually large enough to act as their own system and have interconnected sharing of energy. So these technologies, there are several ways to kind of make these technology commercially competitive, but the main things are to make better envelopes, of course, lower heating loop temperatures. I'll also touch up on that a little bit later on in the presentation. Actually, the next slide. Maximizing energy sharing. Like I said, there's a lot of different buildings in a community, and there's different energy usage. So sometimes a building needs heating, and other buildings need cooling. So you can kind of, in a way, energy share, because they usually expend the heat, and that heat can be used elsewhere in the community. Let's see, what else? Oh yeah, there's also the integrated planning, where in a community there's different buildings. So planning these buildings and how they are interconnected is something that we definitely need to do in a district energy system. And of course, we have to kind of look at it as a long-term investment. If we only look at it at a short term and looking at savings within like 1 year, 2 years, it's probably not going to work. You have to look at it as a long-term, because that it's a more of an operational benefit. Okay, next up, there are 3 main types of district energy system I want to talk about today, I guess the first one, I'm not going to talk too much about it, but the steam and chilled water system is currently our main Enwave system in Toronto. That's uses steam and uses chilled water from our lake as our main source. And the next one is the hot water and chilled water system. We are doing a future upgrade in our main system that would actually have hot water and chilled water provided through a heat pump system. But this is a more upgraded version where all the heating, all hot water and cold water are kind of relatively lower temperature in the hot side and higher temperature in the cooling side. So it's more closer to the ambient water, which is the 3rd level, which is kind of a newer generation of district energy where you're going to have ambient temperature water going around a district. So this ambient water system at the end is relatively low temperature compared to, of course, hot water, but it's relatively higher temperature compared to like chilled water. So because it's roughly around ambient temperature, you have a lower loss in terms of delta T. So that's why it's a better system in terms of the losses, like in terms of longer distances, etc., because you have less losses. And most of these systems that implement ambient water, they would have to have a heat pump at the place where you need heating or cooling. So it's kind of like an ambient loop with heat pumps at the end. So here are some diagrams that I want to kind of go through. So this is like the hot and cold water system, similar to the steam and chilled water. So for this system, we have a heat pump, and there's some sort of energy source or sink that would provide the cooled or chilled water or hot water. And of course, you're going to have the district pump that would provide the flow to the buildings. So it's kind of like this configuration. So the other one is the ambient water system, which is just one pipe, one big pipe where you just put in, you're just trying to maintain the temperature at a certain, like a certain degree. So that tempered water would go around, go to the heat pump, and the heat pump would either take that water and heat it up and drop it back down and drop it back down into the actual main loop, or it could take heat from the water and cool down the water kind of onward in the pipework. So this ambient system actually comes into, there's actually two types of ambient system. There's one that is a single pipe, and the other one is a double pipe where there's inlet and outlet. I don't really go too deep into that two types of system, but if you have any questions, feel free to ask. Okay, so a typical planning process. How do we plan for something like this? So first off, of course, we're going to have a kickoff for the project. Generally a kickoff meeting with the developer or with the client, and we kind of talk through what we're planning to do and what we can look into and what they want in the system, like what their plans and what their goals are for this community. So next, we kind of identify the building and the energy use of that building. So sometimes developers like to build a bit more higher end envelopes, so we need to know that. Some don't want to, and they just want to build to the code. We need to know that as well, so that we can plan for it. Next up, another consideration is, of course, the energy sources around that area. So this is kind of where the ideas come in. Like, there's a lot of brainstorming. No idea is completely silly. There's no silly ideas. We look into, of course, sewer heat recovery. We actually look into sewer lines, whether we can actually take heat from there. We look at the water, lakes, underground, everywhere you can think of. We kind of brainstorm and see if that technology is around and if it's feasible. And of course, after we brainstorm and figure out where we can get these energy sources, we have to analyze it and analyze the different sources and figure out the concept behind this community, and we have to assess it essentially. So we look at it, whether if it works in a technical sense, and after that we have to see if it works in an economic sense, right? Of course, if something is super efficient, but it costs of buying a country, then it doesn't make sense. If you have to create a nuclear fission plant that hasn't been even invented yet, it doesn't make sense. So we do have to do that analysis to justify whether or not these energy sources is reasonable to be implemented. And next two part is kind of a cyclic a task where we actually do the operating model and find the cost of how much it costs to implement the system and also how much it costs to operate the system, and develop a business case so that we can tell the client saying, okay, this is how it is, this is how much you're gonna save, or maybe this is how much you have to actually pay a bit extra for this premium that would maybe save you money down the line, or reduce the amount of carbon down the line and we expect to save money because of the carbon tax, something like that. Of course, it depends on the scenario. So it's more of a cyclic, iterative portion of the planning process. So we kind of go back to the client, come back, and then we revise it, change it, and then go again, and kind of goes around. All right, the next part of my slides is kind of showing you that projects like this needs people across different disciplines. So different teams kind of come together. We need people that deals with finance, deals with construction, engineering, and have to look into sustainability. And last but not least, of course, the municipal planning and approvals. Anything that we have to build, we probably have to go through the municipal planning. So it's something that we have to look through. So yeah, this slide just kind of shows you all the cross-sectional process, I think. So how do we design to reduce GHG emissions? So first of all, like I said, we have to think big. We have to think of all the sources that we have access to and check to see if this technology is available. That's very, very important. If it's not available, then we can't really use it and can't really tap into it. and assess the economics, because of course, whoever wants to implement this, they want to implement it as a reasonable cost. They don't want to, most of the time, they don't want to spend a million, bajillion, gajillion, whatever dollars for something small, and doesn't make sense, right? So we have to take a look at the economic sense. And of course, first of all, is maximizing the GHG reduction, right? How do we reduce GHG reduction? We have to maximize it. And then, of course, develop a plan to how to do this. Sometimes we need to phase in renewables. We have to phase in other GHG reduction technologies down the line. And as the video said, we can kind of future-proof it. We can, at day one, put in something that is a transitional stage technology, and then later on phase in more renewables, phase in more GHG reducing technology down the line. So now I'm going to go through some examples, some case studies of our projects. So first off, I started off with deep lake water cooling. It's kind of our brand, our main system. Everybody kind of knows about it. So kind of going through this is nice. All right, so we have over 75 buildings connected with this chilled water system. Compared to a chiller system, we can actually reduce electricity use by 80%, which is pretty big if you actually look at it. So we estimated that $220 million, million gallons of water is saved annually, which is equivalent to 350 Olympic-sized swimming pools. That's a lot of water every single year. So that's quite a bit. And next is, of course, we can displace 55 megawatts of Toronto's electric grid power, and which is equivalent to powering 8 hospitals. So that's kind of shaving off the peaks, reducing the load on the electric grid. Next up is a nice drawing of kind of how the deep lake water cooling system work. So first off, we take water from the lake, deep under at the bottom of the lake. It's a bit more not filtered, but a bit less debris. So it's actually better for the water treatment center as well. So when it comes in, the water treatment center filters it so that it's actually drinking water acceptable. And then it goes through the heat exchanger process. So it goes through this John Street pumping station, and it transfers the energy into our loop. And it doesn't really touch the drinking water at all. So it would never mix. It's just a heat exchanger, and afterward the drinking water just kind of goes to your tap. And we also have a built-in redundancy at Simcoe Street cooling plant, and it acts as a topping up in case we don't have enough cooling capacity in our intakes. We have this chiller as a backup so that we can actually be able to provide additional cooling. Chilled water circulates through the building at number 5, so it goes through the building and it comes back and goes through the heat exchanger again. So it's a closed loop system, and the cycle repeats, and that's kind of how the deep lake water cooling system works. And this, of course, this idea came from like brainstorming and try to look at other sources of energy. So without that mindset, you can't really develop something this awesome. So this is kind of like the district cooling system. We are looking at opportunities for heat recovery. So this is an idea kind of sharing energy. So if you remember the deep lake water cooling system, it goes into the building and comes back a bit warm. Right? The water from the heat exchanger is let's say 4 degrees cold, and let's say go to the building, it warms up, it comes back at let's say 10 degrees Celsius, right? It warmed up a bit. That means there's some heat energy in there. So there are ideas where we can actually use heat pump on that, let's say 10 degrees water, and would be able to take advantage of those waste heat, right? Of course, temperature fluctuates over the year, and of course, we would have to take account of that, but that's kind of generally the idea. So that idea brings me to this. This drawing here might not mean anything much until I explain it. So this is on the right, let's see if my mouse works, on the right over here. This is kind of our main system, and over here on the left, which is the wet side, is the well. Not sure if you guys heard of it, but the well are developing a new connection there where we're going to implement this heat pump system where it's going to be hot water and cold water, hot water and chilled water system. So it's the second one that I was talking about when I was talking about the 3 district energy system. So in this system, we actually use some of the heat that we accumulate, and we can actually put that in a storage system that we're actually building as well. So under this building, this is something that we're implementing right now. We're actually drilling that hole, and we're putting in a thermal storage system, which would store the heat during, let's say, the winter, when there is, let's say, low electricity costs and there's not a lot of heating requirements. Let's say during the evening where there's not a lot of heat needed, but we're still generating that heat, we can actually store it temporarily in a storage tank. During the summer, we can actually do the same, and we can have a tank for cooling, right? We can store the cool energy, or not energy, but lack of energy in there, right? So this is kind of an interesting system that we're implementing, and it's going to provide peak shaving capability as well, because you're not going to be needing a lot of chillers during those peak times, because you're going to have a storage system that can cool your buildings, so you don't actually need a chiller to operate during those times. So not only does it actually shave the electricity peak for the grid, it actually saves money as well, because during those peaks, it's the most expensive times. So this system is kind of cool. So here are some pictures that we have for the building of the well. So over here is kind of like where the foundation is, everything. And over here is where that highlighted place is where the thermal storage system is. So let's go a bit closer and let's take a look at it. All right, so this is how it looks like from I think it's like a 2nd story looking height. So this is how it looks like right now. And that, of course, is the hole, right? So this is the excavation period, excavation time. And so this is what it looks like during the construction. And right now you can kind of look how deep it is. And this is from the bottom of the well. And this is just 100 feet down, I believe. So this is the excavation of that tank still. And this is still another picture of the 100 feet down. So I believe this thermal storage system is supposed to be having, like the excavation, the final depth is about 250 feet. So this is a very, very deep hole and a very, very wide hole for this thermal storage system. So the key point to summarize is deep lake water cooling actually serves over 85 buildings, reducing peak by 55 megawatts. Eco-cooling reduces over 360,000 gigajoules of natural gas combustion per year, and that part was the heat pump part. Like that part where I talk about where the heat pump uses heat recovery. It actually has the ability, we're planning to have the ability to reduce over 360,000 gigajoules of natural gas combustion per year. And the thermal storage tank is an 8.5 million liter tank, which can serve over 20 million square feet of mixed use space. That's pretty cool. So after this, I finished talking about Toronto. So let's take a look at other projects that is more catered towards the CEP team, like the community energy planning team, where it's not connected to our existing system. So one of them is the National Western Center. It's a brand new place. We don't have any district systems there originally, and we planned this from the ground up. So it is a 250-acre full build out of this whole development, and there's going to be 4 partner facilities on campus. These partner facilities includes universities, includes the Denver Stock Show. It's pretty cool. It's an annual I guess convention. So there's going to be a convention center here, and there's going to be a bunch of cool things. There's 7 main facilities for district energy. So there's different colors, and of course, I'm not going to go through all of it. And the main factor over here is that there is an enormous wastewater pipe and an interceptor that goes around this this development. It's actually this pink, purplish, magenta-ish color that goes right beside this river. So this is an interceptor that has a lot of that energy that is being kind of compiled and funneled into this one big interceptor. It's I don't have a picture of it, but apparently it's a size as tall as an average person. That's how big that piping is, and half of that is already underground. So the other half is as tall as a person. So that's how big that interceptor is. So it's actually the main interceptor through Denver, where it actually gathers all the wastewater, like a sewage wastewater, from all the development around that area, and it goes through this pipeline. So in terms of energy, we were thinking about it, and of course, there is a lot of energy. If you look at the temperature here, here's a graph, a temperature graph of this wastewater. It is actually relatively warm, and it's not too cold, but you can still reject a little bit of heat into it. So for this, we are able to actually provide twice the energy to supply the campus. So that's a lot of energy. So we actually would be able to use this interceptor to heat the whole new development, which is pretty cool. We just have to implement heat pumps and use that energy in order to supply an ambient loop system for this district. Right? So there are a few process partners throughout this whole process. It's been announced that we have, I think we're starting construction already. So it's a cool project that being going along relatively well. So in terms of design process, we have the energy model and we have to validate loads. First part, like I had before, in the other, I guess, flow chart. So deal with the loads first, and next we have to establish the baseline. So we figure out what do we want to do, what kind of technology is there, figure out like what we want to plan to do in this development, and also take a look at the costs and everything around that. Next is develop whether or not there's any alternative. So if there's any alternatives, in any case, like let's say we can't get a permit to tap into the interceptor, the sewer pipeline, what do? Like we have to figure out like what the backup plan is. So in case we can't do that, is there any other options, right? There's a river beside it, can we use that? So there are other things that we can actually look at. In terms of performance and cost modeling, there's of course different parts of it, like the building system, how to do the central plan, the distribution, as in like the huge pipework that links all these buildings together, these 7 major buildings together. How do we do that? Where would the central plans be located as? All of this has to be part of the design. And the alternative comparison, we have to compare this to any alternatives that the developer might do. Like for example, if you look at a regular building might be just a regular 4-pipe system. That's an alternative, and we have to compare our proposed case with the alternative to see if it makes sense to use this proposed case, and we have to convince. Right? We have to be a bit convincing in terms of that. So at the end of the day, we have a preferred design with this sewer heat recovery system, and we can take a look at the loads of this whole development, right? This whole district. We can see that there is actually a bit of simultaneous load, meaning that there's both heating and cooling in certain hours of the year, meaning there's demands in separate buildings that require these, and we can actually meet them without using a lot of energy. We just use a heat pump with that would act as a heat recovery system, where you, on one side you're supplying heating, and the other side you're actually supplying cooling on the other end, evaporator or compressor, depending on which. So there is a simultaneous load in this development, and we can actually take advantage of that. So there are a few alternative cases, like I mentioned before. So there's an alternative where we do 2-pipe system, like a standard one where there's a boiler and cooling towers, and kind of you can take a look at the CapEx, which is the capital cost, and the O&M, which is the operation and maintenance cost, and the utility cost as well. So kind of see that, I guess alternative 1 is pretty high, and then the other version was a 4-pipe system with boilers and chillers, still relatively high. Option 3 was the sewer heat recovery, boilers, cooling towers, And the last one was the sewer heat recovery with heat pumps, boilers, and chillers. So this one was actually cheapest, right? But of course, it doesn't have any heat pumps. So this one is an alternative option that's a little bit higher end, but it also provides, it doesn't have GHG emissions, and also provides some added benefits compared to the two other, I guess, traditional system where there's only boilers and chillers. So this is, of course, the better case. So what's the deciding factors for an ambient system? So the load density, like how compact these loads are, right? An available utility corridor is if there is already a pre-existing utility corridor, we can actually take advantage of that trenching. So what I mean by that is, let's say you're building a new development from brand new, from ground up. You have a bunch of soil with no electrical wires, no pipelines, no anything, right? Generally, you have to actually excavate to put in that, let's say, internet wire, electrical wire, et cetera, and because they're already trenching, we can actually take advantage of that and put in our district pipes along the same trench. That actually reduced the cost for us because we don't actually have to trench our own trench. So that's some sort of benefits when dealing with district energy. We can actually combine these benefits to reduce the cost overall. Mechanical room span. Sorry, water. Mechanical room space. So district energy system actually reduced the mechanical room requirements. You don't have to have a mechanical room in every single building. A lot of these buildings, or actually a lot of developers in general, want to have that rooftop building, like rooftop penthouse. It's one of the most expensive buildings up there, expensive real estate space. So by connecting to a district energy, you can actually save a lot of mechanical room, or a lot of space just from that mechanical room. So that's another benefit. Another thing to look at is, of course, development schedule. If your development takes forever to build, there is no point. If it takes like maybe 5 years for a regular building to be built with a standard traditional method, if it takes you 50 years, then a developer might not want to look into that. Life cycle costs, what that means is generally taking account of the equipment, how long that lasts. Sometimes, in the case, let's say, of the geothermal systems, you don't have to maintain the actual loop, the geothermal loop itself that much. There's minimal maintenance. So sometimes that actually outlasts a lot of equipment. Not sometimes, but most of the time it actually outlasts a lot of the equipment. And we have to take that into account as well. Operation step strategy is kind of how do we combine benefits together so that we can actually operate more efficiently and, of course, more cost effective. Right? We have a smaller plant, a centralized plant, instead of multiple different plants in every single building. We don't have to hire individual people to go to every single plant in every single building because there's only one plant. So we have a centralized operation location, right? And it can also be remotely monitored and operated. And there's also future flexibility in an ambient system. You can add in other lower temperature sources, for example, like geothermal. It's a little bit lower temperature, closer to a sewer heat recovery system. So that's why ambient systems are usually a beneficial system where you can actually tack in additional things along in the future. It's more like future-proofing it. So this is kind of like a quick design sketch of how it looks like. So you have a cooling tower here, the interceptor, which is the sewer main line. You have a bit of screening, which actually screens out the debris from the sewer. It's a waste system, so there's a lot of debris. We screen it out, it goes through a heat exchanger, and then that gets pumped. And if it doesn't have enough energy, we of course have boilers. It gets pumped through the heat recovery chillers over here and supplied to the building. All right, so key points. MASc plant is for 250 acres at Denver. We will have 100% renewable energy. Like I said before, it doesn't really have much energy, and that boiler that I have there is electric boiler. So 100% renewable energy, and the wastewater heat recovery system is the main part, and this is also an ambient system. So that's kind of like the key point that I want to highlight. Next one, this one's going to go quick. This is an ice storage system in Chicago. I mentioned that there is a thermal storage system in the well in Toronto, but this one is the biggest ice maker, I guess, in a way, ice maker in Chicago. We serve 120 buildings and equivalent to 48 million square feet. And it's interconnecting all the downtown plants, or 5 downtown plants. There's 8 trench miles of underground piping, 101 tons of chilled water produced, and which is equivalent to 315,000 ton-hours of thermal storage capacity. We're the largest.
King, I don't know if you saw, but Ruben asked a question in the chat. Do you want me to read it out to you?
Yes, please, because I have my screen covered.
Yeah. It says, for the sewer heat recovery systems, what kind of solid screening systems are you using or propose to use?
We're using a not off the shelf, but we are collaborating with a company that provides this system. So it's a screening system that's already attached to this whole package for this sewer heat recovery. So it's combined with that heat exchanger. So I believe the screening system, it is just some sort of filter. I'm not sure. I didn't really look too deep into it, but it's some sort of package system with the heat exchanger. If that answers your question. Probably not, but I don't have too much information on that. Sorry about that, but yeah, I could probably look into it. But at this moment, I don't have an answer for what specific type of screening system.
Great, thanks, King. I'll interject if I see more questions.
Okay, thank you. So how it works is there's a bunch of buildings, and there's a chiller, and you literally build up a water, and you cool that water so much that it turns it into ice. It's essentially a giant ice building system, which is pretty cool. And of course, there's different, there's different cells of ice packs. So you can actually say that this ice pack, let's use this first, and then we're going to drain it, and we're going to use that water for cooling, and then we have, like, let's say a few more storage cells, and we can actually use these cells strategically so that we can actually use them all, and we can actually circulate that energy around. So we would be able to use it. So it's kind of interesting. I don't know too much of it because this is an existing system for a while. So it's kind of the coolest system ever because you're building a large amount of ice. So here's a few key points that I kind of mentioned in the beginning. So I'm not going to go through it too much, but it's 315,000 ton-hours of ice thermal storage energy, which is pretty cool. Okay, so I have one last one. So this is residential geo exchange, because right now I've been only talking about like big districts, big high rises, condos, commercial buildings, nothing really on houses, right? Like a lot of people like to live in houses. They like to have buildings like this, right? How do we connect this as a district system, right? It's hard to understand, but we've collaborated with Markham and Mattamy to develop a community up in Markham called Springwater. This is our first low-rise residential district energy system, and it's one of first of its kind. And it uses geothermal energy. Here's a quick picture of it. It's essentially a geo-exchange system. We have geothermal boreholes underground. It's really rough drawing, but you can kind of see the red lines going deep underground in the right-of-way. So we're putting these boreholes in the road so that it doesn't take up any other space. It doesn't take up room in your house. It doesn't take up room in the parks, so that so in case anybody wants to dig under there, it doesn't destroy our piping. We'd like to put it into the road. And we have pump vaults that actually circulate energy around the whole community. And this energy, or this system, is running on ambient temperature district system. So it's just one pipe. We're feeding in water at a relatively constant temperature, and we're trying to maintain that with the geothermal boreholes. And these boreholes are cool. They're relatively deep. They're 850 feet deep under the ground. So it's relatively deep. With all things considered, it's a geo exchange system. It's not like geothermal thermal, as in like you're not taking in like high temperature from magma. We're just exchanging energy into the relatively cold ground, but it's not freezing. So it's roughly around 10 degrees from the ground, and we use that. So here's a quick picture of what it looks like. It's our first residential district system, low-rise district system, like I said, and it's recently has its sales officially announced, and it's started. It's pretty cool, and I'm very excited to see what's going to happen. And there's about 300, a little bit over 300 residential customers. It's, like I said, geothermal, heated and cooled. And it's an ambient system, and all these houses are nearly net zero, meaning that it's relatively efficient. The envelope is efficient. The building to, I believe, Energy Star. Well, Energy Star has like a prescribed and stuff like that, but they have it a bit higher than that, closer to near to net zero. But they need, I believe, solar panels in order to be officially net zero houses. So they're relatively efficient, and they're reducing over 7,400,000 kilowatt hours of thermal and electrical energy compared to the standard Ontario Building Code houses. So that's quite a bit for 300 homes. Right. So next up, I have a quick activity that I want to kind of go through. So I want you to kind of calculate the carbon emission for a system. So I haven't really talked about too much about carbon. So let's kind of go through this activity to figure out how much carbon emission would be, I guess, reduced for a standard system, a proposed system versus, let's say, a business as usual case. So I have some GHG intensity assumptions over there, kilograms of equivalent CO2 per kilowatt hours of natural gas equivalent. And we have the kilograms of CO2 equivalency of kilowatt hours of electricity. And there are some base case assumptions and proposed district system assumptions. So I have here the heating energy consumption in terms of thermal energy. I convert it into kilowatt hours. Let's say it's 5,662,000 kilowatt hours. Natural gas furnace with 85% efficiency. It's not as efficient as I believe OBC. I think right now the new code is 90%, I believe, for SB12. I don't remember right now off the top of my head, but let's use 85% for now. Cooling energy consumption, 1,474,000 kilowatt hours of thermal energy, and let's assume that the air conditioner has a COP of 2.9. Okay. On the other side, we have a proposed district system. We have a heating energy consumption of 2,948,000 kilowatt hours thermal energy. It's a bit lower than the other one because this is more, let's say, the building envelope is better, and the other one is just baseline, and these are base case numbers, and the proposed case are like highly efficient buildings with very top of line building envelopes. And the district system plus the heat pump has a COP of, let's say, 3.1, and while the cooling energy consumption is 1.4 million, it's close to the OBC code. Cooling energy doesn't really change that much, and the district system with the heat pump has a COP of 4.5. Let's do this quick exercise and try to figure out how much carbon emission reduction it would be if you, let's say, go with the proposed system compared to the base case. Okay, so I'll give you guys a few minutes. It's going to be a multiple choice, and I'm going to probably try to do that. How do I do that? I'm going to put a quick poll. Let's see, multiple choice. If you guys have any questions, feel free to ask. But yeah, it's just a quick activity. You just type up the answers. Great. So I just have for answers randomly typed. One of them is a real answer. I want to see if you guys wanted to calculate it and do this. And of course, if you have any other questions on the other slides, anything you want to ask, feel free to ask as well. Haven't spoken in a while. My throat is already dry from just talking. All right. Kind of go through. I'll go through it in a moment, maybe just another minute or so.
I guess before you move on, King, if you're still working on it, please put your hand up.
Oh yeah.
You can put your hand up in the chat so we don't, if people are just need more time. And if you don't feel like working on it, just guess a random answer.
That is fine too. I'm also gonna go through it and kind of also provide the real answer. But yeah. Okay, so there's a question. What's it? How common are district energy opportunities in a typical city? How can interest in such system be stimulated? Good question. How common are these in district energy? Of course, it depends on the developer and also the city. So sometimes I know that there are cities that are very, very interested in district energy, and they are looking into it. And of course, because of the rising concerns of climate change recently, kind of sheds a light, like especially the pandemic, how everything kind of went a little bit better when everybody stopped working as much, or not working as much, but less transportation, there's less greenhouse gas emission, kind of see the effect. So a lot of cities actually are looking into district energy. I know of there are a few that are in discussion. They're trying to get a bit of capital, and of course it's a little bit harder to kind of gauge how common they are. And I personally think that it would be up and coming, and especially because district energy is kind of combining all the buildings together. We're sharing energy, and in a way, the developers don't have to worry about that piece, right? That piece of the design is gone from their hands. So it's something that benefits both sides in a way. And of course, cities are interested in it because it reduces their GHG emissions and it helps them reach their city goals. And a lot of cities have a GHG reduction goal, and district energy helps them a lot with that. Okay, so I think I'm going to stop. All right, not a lot of people answered, but that is fine. All right, let's kind of go through it. I have this typed up, but I didn't really need it. The actual answer is about 1,162 tons of equivalent CO2. Okay, so here are taking up the answer. Here's me trying to take up the answers. So over here, I kind of divided by 0.85, which is the efficiency. So this is how much natural gas equivalent you would actually need. And this is the electricity for the cooling side. And then you just multiply the GHG emission intensity with this. You get equivalent CO2. You just sum it up. On the other side of the proposed case, you kind of do the same with the COP, et cetera, et cetera. And you can find the emissions that way as well. After you subtract it, this is what you get. It's relatively straightforward, and stuff like that is important to the city. So I'm going to wrap it up here.
I have a question about the why does the proposed case initial thermal load, why is it so much lower than the base case thermal load?
Good question. Yeah, so for base case, generally we look at what the builder would typically build if to code. So for this one, it's a more special case where we're comparing it with like our code buildings. Generally, it's not that much different. Sometimes it's slightly a bit lower because we're proposing, let's say, a little bit better windows, and we'll convince them to have better windows so that we can actually reduce certain costs, let's say in the geothermal side. So with better glazing, let's say with better windows or even a little bit better insulation, you might get a bit benefit in the other buildings, like other capital cost sense. So there are benefits that way. But in this example, I used a case where base case is just building code standard and proposed case is like net zero kind of thing. So this is kind of like a big comparison. But typically it's a little bit closer to the base case, like in terms of energy consumption.
Mm-hmm. Great,
in terms of energy requirements, not the building energy consumption. Does that answer your question?
Yes, thank you.
Okay, perfect. Okay, so to sum it up, so this is kind of like my conclusion. So what's the success factors? So we have to get the right team around the table. We have to have a project champion, right? Someone on the other side or even on our side to kind of champion this this project so that they keep on top of everything, find the top decision makers, trying to get everybody together and in a sense manage this project. We need someone to do that. And we have to integrate energy planning at a very, very early stage. You can't just go in as a developer and think of it like, oh, I wanted to build a building and I'm not going to ask anybody about energy until the month before we're starting building. Like we're not going to be able to design something at that way. So we actually, in order to develop something that would reduce carbon effectively and with nice ideas, we need a sufficient time at an early stage in order to develop. And another thing is include construction expert at early planning. So when we plan stuff, we like to bring in construction experts. So we have to bring in people that know what they're doing and know what they're actually constructing. And the reason behind that is, let's say we're putting geothermal boreholes and we're putting geothermal system into the ground. We actually have to work with the construction team in order to, in a way, leverage some efficiencies, right? Like I said before, if we trench at the same time and we put the piping at the same time, we reduce some costs, right? And let's say we do other ways of trenching. Let's say in terms of horizontal, let's say we had to actually grade the whole site, and we have to dig a bit of trenching in order to put in the horizontal pipe work. Maybe we can actually optimize that efficiency by leveraging some other digging that they have to do. So working with construction expert at the early stage would actually definitely help. And maximizing energy sharing, so how we look at how much buildings and what type of buildings we have to use that and how much they share energy so that we can reduce the amount of electricity or let's say natural gas we need in order to provide the heating and cooling, right? By energy sharing, it's the most efficient way to provide the heating and cooling for the buildings because you're not actually pulling that from any other sources. You're just kind of passing along that heat to your neighbor in a sense, and you're passing along that energy around, and you're sharing that energy to where you need it. Another point is invest the time in energy model and calibrating the model with real data. If you go in blind with a relatively close model and it's not really accurate, you can be wasting your time, and you could also be wasting, or you can actually create a system that is not optimized and it's not what the customer would actually physically have, right? So we need to invest quite a bit in terms of the energy model. So that's kind of a big part of everything. Energy model is really crucial in terms of designing for reducing GHG emission. We have to know where we can actually cut a bit, like let's say we can save a little bit of energy here and there. And the best way to kind of reduce GHG emission, of course, is to reduce the energy consumption, right? So by looking at the energy model, we can actually provide some recommendation and say to reduce this, like do this, maybe change the shape of it. And we can actually work with the developer to do something like that and reduce GHG emission at the end of the day. And of course, electricity and cost. And last but not least, we preserve the optionality for future optimization. So by this sentence, what I mean by that is we have a centralized plan. We have to make sure that in the future, we have the capabilities of switching out new technology into it, right? So for now, let's say we're thinking of geothermal, right? Like we're putting in geothermal and it's providing all the energy. But in the future, because of climate change, it might change when we need other sources to supplement any changes in climate, right? So we need to have that flexibility to add in additional systems. Like for example, let's say we have to add in like a solar collector or something, or we have to add in river water in order to supplement the cooling. We have to have that opportunity or that method or that availability so that we can actually, in a way, look into the future and future-proof everything. So that concludes what I have. If you guys have any other questions, please feel free to ask. Oh, Jim has a question actually. So there's energy into existing building in an established city. So that's a very good question. To install a district energy to existing building in an established city. So this is kind of a little bit hard. So we have to slowly expand. Like for example, I'm giving you an example in the Toronto system. So we have to slowly expand our district loop in order to even provide energy to those outside of our district, right? So if you're a bit too far away, we can't really connect it to the existing system. Like for example, if you have a building in Markham and our system is in Toronto, we can't really connect to it. It's a little bit way too far. It might take some time to get there, even if we try our best, right? It's just super far away. So another solution is to have an existing system there that you can connect to that's nearby, right? So it's a little bit harder in that sense where it's pretty expensive to dig up the road in order to put in the pipe work for a district system. So that is, it's definitely hard to do so in terms of feasibility in that. But of course, let's say we have that Markham residential building, that community with that 300 townhomes, or 300 homes, not just townhomes. There's 300 homes there, and that connection, you can actually connect other buildings down the line if we kind of, in a way, expand that system, right? We still have to include cost in additional geothermal boreholes, but we have the opportunity in the future if we do want to do that, and people are interested in doing that. The only problem right now is also like, well, not the only problem, but one of the problems is also the interest, right? So in order to put in this infrastructure, people have to be willing to be part of the system, be willing to be connected to the system, and that is also another thing too. Have you considered the difference in overall maintenance costs and what's the comparison? What happens at the end of the life of the system? How would it be replaced? Good question. So yes, we do take account of the overall maintenance costs. In overall, let's say a standard system, you have the chiller and boiler. Let's say it's a typical residential building. You have a chiller and boiler system. Generally, nobody, when we speak to some developers, they said that nobody even do regular maintenance. Some don't do that. Some do minimal regular maintenance, and that usually don't really extend the life of that equipment that long. So in a district system, we do regular maintenance because it's so centralized. It's relatively easy to kind of go into one place, do the maintenance in one place, right? So in terms of cost and maintenance, district system is definitely cheaper. The pipework, you don't really need to maintain it. It lasts for 100 years or more. Technically, it's more, but on paper, it usually says it's 100 years of life. Like it lasts for 100 years typically, and it's similar material to water, like the drinking water. So as long as your drinking water system lasts, our system is supposed to last as well, and that goes for any other district nodes as well. So what happens at the end of the life of the system? We, for a district system, we typically, of course, renew the machinery. We normally build in an N+1, meaning that if one chiller goes down, we have like a redundant chiller so that we can actually kind of, in a way, have this running, and we can swap up this one that's broken or swap up this one that's near the end of life. Even though it's working okay, we might have to replace it if we see that it might have problems down the future. So like we do replace these, and we do have N+1 so that it doesn't completely shut down the whole system, right? Because we are considered utility. We don't want to shut down heating and cooling, especially heating. It's a life-threatening thing, so it's something that we would definitely do. And yeah, during the replacement, we kind of find a time where let's say the load is not that high. We're not going to purposely switch out a heat pump during peak heating seasons because we might actually need all these heat pumps, right? We're picking a time where it makes sense to switch these out, and we do the maintenance that way. And okay, I hope that answers the question. Next question is great information. Another recent example of ambient system based on geoextreme is in Blatchford DES in Edmonton. Okay. So, oh, okay. That's interesting. Yeah. So you guys have both geothermal exchange and sewer heat. That sounds awesome. Yeah, I'll definitely reach out and try to understand how that system works as well. Okay, I think that's all the questions. Do you guys have any other questions?
I don't see any other questions there. If anyone has it, oh, here we go.
Oh, what are the major challenges in implementing it beside existing buildings, and how does distance and length of distribution network affect the overall system efficiencies? Does it have an explicit place in municipal plans like Transform TO? Yeah, I would say like if it's in downtown Toronto, if it's close to the existing system, it probably if it's not close enough to be connected, it would probably have to wait a bit in order for our system to expand to that point. But we do work with Toronto, like the city of Toronto. One of our projects that are coming up is working with Toronto for the a civic center, like in a way like a town hall, and we're building that system with geothermal. So that one's called the Etobicoke Civic Center. I believe that's also public news as well. So that's also a project that we're working on as a separate node, a separate district, and we're planning to potentially branch out from there to provide district services for other upcoming new buildings. So I guess the major challenge is to kind of approaching new developments that don't know anything about district energy. So that is hard as well. Or maybe new developments that think that district energy is only located in downtown Toronto. I think that's a big challenge. And another challenge is, of course, like you said, existing buildings. It's hard to connect to them unless our service is there. Other challenges are working with city and city approvals. Some new, I guess, technologies such as like the sewer heat recovery would require additional approvals, similar to like the lake water, deep lake water cooling, that needs approval from the city. Everything that's relatively new, that has to go into a approval process that they might not be familiar with. So for example, if we have to tap into the sewer system in Toronto, we would probably have to go through a rigorous process in order to get approved. And similar things like that, like tapping into, let's say, a nearby river, or even going close to a national heritage area, like a natural place, right? So if you want to build close to, let's say, a riverbank, that requires approval, even though it doesn't have any contaminants. A lot of that is new to the to a lot of municipalities, and they have to kind of learn the process and learn how the design works in order for us to actually implement it. So that's definitely a challenge. And we see that in the Markham project. And yeah, and we work through them, and it's not a challenge. It's not a challenge that we can't implement it. It's more of a challenge of the process and how much time it takes to do something like this. And oh yeah, one more question within that was the distance and length of the distribution network. Yeah, I would say yes for I guess higher temperature heating and lower temperature cooling, because you will have, I guess, exponential losses the longer your pipework is, because of course your delta T, you can put a lot of insulation, and that would come in with cost. If you put in a lot of insulation, costs kind of goes up as well. So the best way of going around that is, the best way I guess we found is using an ambient system where it's relatively close to the ground temperature already. So there's not a lot of losses there. And in terms of efficiency, we just have to make sure that we have regular either pump valves that ensures that the flow is consistent and the pressure is there, and also energy reinjection points. So there of course, as the loop comes back, your energy is slowly diminishing. There is a point in the pipework where there's just not going to be enough energy for the next house, or the efficiency of your system would ridiculously go down significantly because of how low the temperature of water coming in is, right? So at regular points, you have to find a way to replenish that energy so that it's consistent. So that is one thing that we have to do as well as a larger distribution district network, especially if you're running in an ambient system. Does that answer your question? In terms of, yeah, in terms of, I guess, overall system efficiency, we're planning to make sure that we always plan to ensure that the efficiency doesn't decrease significantly. Like, of course, there is a change from, like, let's say the first building versus the last building. There's a slight energy difference there, but we basically plan to minimize that temperature difference, right? So that down the line, you're not going to have, let's say you have to pay like $500 more a month just because you're living or your building is like a little bit down the line in a district system. So we put energy reinjection points, I like to call that, so that it maintains a certain temperature and maintains a certain amount of energy within that pipework. Okay, I think that answers that question. Okay, is there anything else? Any other questions that you guys want?
I think you got them all there, King. So maybe you can stop sharing your screen for a minute, and then we'll just wrap up. All right, there we go. So thank you everybody for coming. Thank you, King, for such a great presentation. It was very interesting. If you have any other questions, feel free to contact myself as part of the CSE, or you can reach out to King, or I can put you in touch with King. I don't know if you have his email address at hand, but feel free to reach out and I put you in touch with King. Otherwise, thanks for coming. We look forward to seeing you again in another month, and enjoy the rest of your day.
Thank you.